Hello everyone, I'm Chitra. My teammates are Bhumika, Divya and Grishma. Our topic is performance of ultracapacitors. What is an ultracapacitor? An ultracapacitor, also known as a supercapacitor or electrochemical capacitor, is a device for storing electrical energy which is growing rapidly in popularity. The design and mechanism of operation is somewhere between an ordinary capacitor and a battery, which opens up some interesting and valuable applications. This is the diagram of an ultracapacitor construction where it consists of an ultracapacitor body connecting terminals, porous paper separators, and those are the double side coated electrodes. Next, the ultracapacitor construction. The double-sided coated electrodes are made from graphite carbon in the form of activated conductive carbon, carbon nanotubes, or carbon gels. A porous paper membrane called a separator keeps the electrodes apart but allows positive ion to pass through while blocking the larger electrons. Both the paper separator and carbon electrodes are impregnated with the liquid electrolyte with an aluminum foil used in between the two to act as the current collector, making electrical connection to the ultracapacitor's solder tabs. The double layer construction of the carbon electrodes and separator may be very thin, but their effective surface area into the thousands of meters squared when coiled up together. Then, in order to increase the capacitance of an ultracapacitor, it is obvious that we need to increase the contact surface area. That is A in meters, without increasing the capacitor's physical size, or use a special type of electrolyte to increase the available positive ions to increase conductivity. Then, ultracapacitors make excellent energy storage devices because of their high values of capacitance up into the hundreds of farads due to the very small distance d or separation of their plates and the electrode's high surface area A for the formation on the surface of a layer of electrolytic ions forming a double layer. This construction effectively creates two capacitors, one at each carbon electrode, giving the ultracapacitor the secondary name of double layer capacitor, forming two capacitors in series. However, the problem with this small size is that the voltage across the capacitor can only be very low, as the rated voltage of the ultracapacitor cell is determined mainly by the decomposition voltage of the electrolyte. Then a typical capacitor cell has a working voltage of between 1 to 3 volts depending on the electrolyte used, which can limit the amount of electrical energy it can store. In order to store charge at a reasonable voltage, ultracapacitors have to be connected in series. Unlike electrolytic or electrostatic capacitors, ultracapacitors are characterized by their low terminal voltage. In order to increase their rated terminal voltage to tens of volts, ultracapacitor cells must be connected in series or in parallel to achieve higher capacitance values. Next is the schematic of an ultracapacitor cell, which includes a current collector, electrolyte, porous electrode, and a separator. Performance of ultracapacitor. Like a battery, a single ultracapacitor cell consists of a positive and a negative electrode separated by an electrolyte. However, ultracapacitors store energy electrostatically like a regular capacitor, not chemically like a battery. There is a dielectric separator dividing the electrolyte, also like a capacitor. The small separation between electrodes permitted by this structure leads to much higher energy storage density than a normal capacitor. Whilst an ultracapacitor stores less energy than an equivalently sized battery, it can release it much quicker, as the discharge is not dependent on a chemical reaction taking place. Because no physical or chemical changes occur when charge is stored, ultracapacitors can also be used many times over without degradation. Applications of ultracapacitors. The performance benefits of ultracapacitors come into play most effectively when a large spike in power consumption or a large scale repeated charging cycle is required. Electric or hybrid vehicles to provide a quick burst of acceleration over short distances or to start the main motor. Quick charging electronic devices, waterproof or weatherproof energy storage, example remote wind farms, military vehicles, starter engines for tanks, submarines, compact power for missiles. Thank you.